stuff on the subject of the impact of cybersecurity on our industry is Peter Lemme. He serves as chairman of the AEC KUK band SATCOM subcommittee and industry editor of Project Paper 848 and Broadband Aviation Radio Network. So welcome, Peter.
Thank you. All right, well, good morning. I have a number of slides to talk us through some of the issues that are related to cybersecurity and protecting the aircraft networks primarily. I have a perspective on this, but I'm sure you have a perspective on this as well. And first off, I want to say that this is an educational proceeding. I'm providing information that I believe to be accurate, and the information that I'm showing may be copyrighted, but I'm using it under fair use. So what are you worried about? We have airports with fences, and we have firewalls on our networks, and so everything should be okay. But they aren't. We have malicious activity, and we have maybe inadvertent activities going on that undermine some of the security that we would set up around the perimeter. So I'm curious, for just a minute, I know we won't have time to hand the mics about it, but I'm just kind of curious, what are you expecting me to talk about in this presentation? And while we're doing that, I'll let this video run. This is off of FIREEYE site showing virus attacks around the world. Anybody? What are you worried about on aircraft and networking? Just yell it out. I'm just curious.
Chris Roberts.
Chris Roberts. Did he take control of the auto throttle? Okay. By the way, I was thrust management lead engineer at Boeing for 9 years, so that actually is my system. Anything else? Is that you're worried mostly about passengers uncovering connectors and plugging in with stuff that they've worked on their own and trying to do things?
And is IFE a gateway to cabin avionics for people with mystical?
So like the Wi-Fi access points, are they a gateway for passengers to have some fun?
Yes.
Yeah.
As a current state control of the communication between your plane on the phase one, but not the IFE system, but the plane itself.
So flight controls versus communications?
Yes, or the identification between two planes, modifying one or modifying one.
Plane to plane communication?
Yeah.
Okay. Anything else?
Somebody putting a virus inside the air control.
Planting, staging some sort of an attack for later. This is, by the way, I think one of the biggest ones to worry about. So good. I think I've got all of those. I'll touch on those. I'm not going to answer all your questions, but I'll give you some information, and I'll have a little bit more. Yeah, one more.
Regulatory update on where AEC and FAA.
Okay. Well, then I'm in good shape. Andy, you got one? Sure.
Well, should these things be classified? Defense against deliberate misattacks, and just design it so there aren't mistakes, and so that inadvertent incidents or exposures just happen because you built something that's hard to test.
Okay. Complexity. In fact, I hope I remember to come back to that if I don't. Remind me, because that is a point that I want to bring up. All right, so these are great questions. I think I can touch on those. Before we tell the story, you got to get to know the cast members. Who are we talking about in this environment? Okay, so the first cast member is the passenger. Now, the passenger can actually take different roles on board the aircraft. Typically, they're just looking for service. They want to get from point A to point B. They'd like to have a good time and enjoy the trip. So that's certainly the objective of the vast majority of passengers. They're going to bring devices on the aircraft that have software in it that they may or may not have taken good care of. They may have hardware, by the way, that they may not have taken good care of, but we'll leave emissions to the side on this. So it's possible that passengers are carrying threats inside their devices unwittingly. They don't know that they're a guinea pig for this kind of behavior. You also have this very small category of passengers, which are bored software engineers. And they apparently find a certain amount of enjoyment sitting at their seat and probing about on the network to see what they can find. So the passengers, they're generally well-wishing, but they may inadvertently through their actions, intended or unintended, cause some strange things. Now, Chris Roberts, as it was asked, is one of these passengers, and he did something that I thought was unreasonable and illegal, and that is he accessed part of the airplane he was not supposed to access. He had created a connector and plugged in to a jack that was not intended for passenger use. It was clearly something that he wasn't supposed to be doing. And from my perspective, he should be charged with a criminal charge for that, just for that event. And he admits to doing that, and I don't see why he gets a pass on that. The aircraft, by the way, has ports all around it, and I don't know that every one of them has a key around it. And that's something physical security of your network is an issue. So having passengers wandering around thinking to plug in, that's one thing to have your public Wi-Fi protected, but now you're starting to have the potential of coming in behind the scenes, getting into networks that you shouldn't have access to. So hopefully every airplane, every airline has taken a good study of this, and they've got some ideas on how to protect the ports. Because that's really just unreasonable to have that behavior. So then we have the pilot. Now, surprisingly, the pilot isn't always thinking broadly. They have a tendency of thinking about their own problems, and so not every pilot. And I don't want to paint this brush too broadly, but there are pilots out there that will push the rules a little bit. I had a pilot that routinely called me on his cell phone when he was in service, flying. Where are you today, John? Oh, I'm over Spokane. You know, he wanted to talk about committee work. So pilots have a job to do. They're anxious to learn how to do that job the best way they can. Not everything in an airplane is published. There's a back channel between the pilots. They learn little tricks on how to use the airplane that not everybody knows about. There's a little black book every pilot carries that has their little tricks that they learned about from other pilots. So it's an interesting group of people. Now they now are also bringing devices on the aircraft, these are EFPs, and I'll talk about those. Air traffic controller, I'll pick it up a little bit. The air traffic controller, their job is pretty straightforward. There isn't a lot of things going on in this framework. The controller gets very anxious when the pilot can't be reached or the airplane isn't where they think it should be. And so the controller has a tendency of getting excited in those events, but otherwise, you know, they do their job. Aircraft mechanic going out to the airplane. The mechanic is the one that is going to have to do the software loading and do the debugging and so forth. And this now becomes an avenue. They have access to the airplane, all parts of the airplane, and they have the ability to load software on the airplane. So the aircraft mechanic has a major role in network security, and especially as we go down into, and I won't get into it, but when we talk about keys, managing keys, the mechanic's going to have a role for this. One thing in the IFE industry that I'd like to kind of harp on is the use of common passwords, role-specific passwords. So if you come up to an IFE access panel and you're a maintenance tech, you may have credentials that are for a maintenance tech, but it's a generic set of credentials. Every maintenance tech in the airline has the same credentials. In fact, that IFE supplier may have the same credentials on every airplane that they ever built. I won't go into passwords inside the system, but just basic access to a terminal to make changes on the airplane, there's no authentication, is what I'm getting at. Anybody who has this password can come in and get access to do these things, and there's no track to say who actually was in there, were they authorized to do that. There's no repudiation, there's nothing there. And that's pretty much, by and large, the way the airplanes are worked today. It's a very trusting environment. I'm going to say trust a number of times. Every time I say trust, you should cringe. Okay? Flight attendants. So flight attendants now have connected devices. They're managing credit cards. They also have logbooks that they have to make entries in. These logbooks certainly have a factor in the maintenance of the aircraft. So flight attendants are becoming more and more connected. Again, just like with the pilots, there's getting to be more and more mobile devices handed out to the flight attendants. So you have this large population of employees that are carrying fairly sophisticated devices, and any enterprise knows that that can be a little bit of a challenge, kind of making sure nobody does something weird. Air marshals. We do carry air marshals here in the United States. I honestly don't know much about it. I do believe that there are private networks set aside, private SSIDs and the Wi-Fi that they can access, nobody else can get to. They're hidden. That they may have connectivity that exists below certain altitudes that passengers wouldn't have. I really don't know, but I'm just guessing on this. But the bottom line is clearly authentication is very important to a federal air marshal. They don't want to have instructions being given to them that aren't from their boss or from their authority. That's kind of the fundamental aspect of that aspect. In-flight entertainment. So in-flight entertainment represents a huge and rich set of equipment and functions and capabilities. It's constantly changing. It's the most up-to-date on the airplane of everything we have as far as network capacity and so forth. It's state-of-the-art compared to anything else in the airplane. Content, managing content has been a big issue. Clearly, certainly early window content, but content in general can't just be left to anyone to have access to. There's been a lot of concerns about the encryption of content in transit, and then once it gets to the airplane, how is it secured on the airplane? Does the server hold the keys as well as the content, just in some obscure manner that hopefully you won't find? Those things are happening. And then transaction processing. So any of the in-flight services aspects that are billed through the in-flight entertainment creates a liability in managing, and PCI certainly is a factor in making sure that these networks are secured, but it's an area of concern. Aircraft systems themselves. So we're moving, we've been connecting aircraft systems to the ground. We've been doing that, at least I could say I've been doing it since 1990, but it's been around for a long time. There's no news here that aircraft systems are ACARS goes back to 1978. So we've had data linked to the airplane, sending messages from the pilots. With the advent of the 747-400, we had maintenance messages, and we've had airplane health monitoring for quite some time. So this has been going on. But we're apparently at the point of a huge change where suddenly, where we were getting a dribble of data, we're getting, a fire hose of data. And this information generally is outbound from the airplane, but it can also be to the airplane itself. And this is where we get into data loading, configuration control, as well as airplane health monitoring. But what's apparent is more and more LRUs on the airplane want to be connected. In fact, I was in a talk somewhere else where somebody said that was the sort of the bellwether of the development was, well, what's the connectivity feature for this device, whatever it was, a billboard, how's it connected? And so there's a rush to provide connectivity to everything. And what we have to do, of course, is make sure that that doesn't create a pathway to bad actions. Baggage has been, I think, probably one of the most feared areas, and of course, the events in Egypt are pretty sobering. I hate to speculate on these things, but the Russians are being very adamant that this was blown up. So bringing explosives onto the airplane into the cabin has been a challenge, but bringing explosives in through check bags has been certainly an area that people have had some, I don't know what, it's not success, whatever, they've been able to do it. And we right now, if you sign up for a connected application, you always have to go through CAPTCHA. Why do we do that? Because there's concerns about having devices that would wake up in flight and connect over the in-flight systems, and then a trigger could be sent remotely. Now, honestly, people are pretty sophisticated. You can sense altitude. You can do all these kinds of things right now. So this CAPTCHA thing, it makes us feel better, but it's probably not going to stop anybody for a half a second if they really want to do something like that. But nevertheless, I think in the future we're going to see bags being connected. I expect to see every bag to have some form of a beacon on it at some point. We're going to be able to see every bag as it's loaded onto the airplane and progress through. It's all going to, we're going to see connected bags here very quickly. And similarly with catering, just in the instance of trying to move things along quickly, the idea is that every little truck, every little cart or whatever, will have connectivity inside it. Every one of these connected objects creates opportunities. We have rules and regulations. I'm going to talk about them. I'm not going to dwell on it here. You have the aircraft designer, which I'm representing in this discussion probably most, but the aircraft designer is really only affecting the aircraft until it goes into service, and then it gets into the hands of the operator. And there's a big difference in the view of how the airplane was designed versus how the airplane is operated. One would think they're exactly the same, but they aren't. Tabling service providers. All of this information is going into some repository, whether it's centralized, like in the case of ACARS, we have Eric and CETA who take that. But we also have, within the teleports, we have a certain amount of processing, and then, of course, depending on what kind of service you're going, there's more processing. So it's a very distributed methodology. Data link service providers build their business on delivery of data. That is what they do. And of course, anything that jeopardizes that is a threat to them, but they're also a target for any kind of nefarious acts because basically all of this information is coming up through their facilities. So they represent a bit of a target. The owners of the corporations that run all of these types of businesses, whether it's an IT company, whether it's a content company, whether it's an airline itself, at the board level, everybody has a lot of concern about network security, and what they don't want to hear is that something has gone on in their enterprise that's allowed them to take a certain amount of liability that's caused them some hazard. So I think the Sony Pictures situation certainly was alarming. The idea that people are using network security as a method for trying to make money or to influence a position is really political position or corporate position. It's out there, and I'm naive on these kinds of things. I like to think that bad people are out there, but they are. And I think the good news is this is a good time to get funding on these kinds of initiatives. It's sort of a hot button issue, and no C-level executive wants their company to go under because they didn't do the things they're supposed to do in network security. So those are pretty much all the good guys. Let's talk a little bit. There's only, I think, really just two fundamental categories of the bad guys. At least that's all I'm doing here. One is what I call the pirates, the people that are looking at networking as an opportunity to make money. So they're driven by profit. They may be driven by commercial or competitive reasons as well, but they're not necessarily out to hurt people. There is another category out there which is truly, let's just call it evil. There's people out there that would like to cause bad things to happen, and they would draw satisfaction from that. Peter Scaves is an engineer at the FAA. He made a presentation to what's called PARC, Performance-Based Aviation Rulemaking Committee. And this is the Communications Working Group. This is where we talk about controller pilot data link communications and automatic dependent surveillance, things like that, air traffic control communications. And so Peter came and gave a little bit of a talk about what the activities are within the FAA. So they talk about ASIST, and so just read what I have in yellow. The conclusion from the FAA is the greatest threat that they're seeing, and again, this is protection of information, so it's not necessarily the protection of the flight control system, but it's more about how information is protected. They feel that the greatest threat is from the internet, so it's that big, the cloud. And they've created special conditions. So if you have an airplane that has connectivity, then you need to demonstrate, and there is no template for what is good or bad. You have to just come up with, on your own and figure out how to convince the FAA that you've got this problem solved. I think it's an area that, you know, that they need to provide a little more guidance. But one of the concerns is, what if the airplane is being threatened from the outside, and the other is, what if it's being threatened from the inside, if it's that passenger? And well, thankfully we got through that problem. So there's a list of, at the transport level, of issues, and I kind of went through the list, and I thought I'd just share that with you. One is, as I kind of mentioned, there's special conditions required on access to any system that has access to a system that's required for safe operation has to have a special condition. Development assurance for complex devices. Now, when we talk about flight controls in particular, there's a lot of emphasis placed on the rigidity of the functionality inside, let's say, a DO-254 ASIC or FPGA that can't be reprogrammed on the fly, so to speak. And that becomes, that DO-254 hardened complex devices becomes a foundation for a lot of our level A equipment. So when we talk about using digital flight controls and things like that on the communication side, we're relying on hardware sort of appliances to protect the network from being, you know, adjusted or changed rather than a software designed approach. And you have to go through a fairly rigorous process to demonstrate how that works. There's also a special condition about ADS-B out. ADS-B out, if you're not familiar, this is a broadcast of aircraft position to the ground and to other airplanes. We've used it in the past for a thing called TCAS, Traffic Collision Avoidance Systems, or AWAS, Aircraft Warning, ACAS. The thing that's interesting about ADS-B is that it is the ADS-B out position is a 56-bit field in that splitter. And there is nothing in there that gives you any confidence that that is a legitimate message. So ADS-B is a really interesting problem. So I'm not going to go into that here, but just kind of watch that space, and particularly things like space-based ADS-B. It all works great, but when you start thinking about other aspects of ADS-B, it starts to get a little bit curious. Here in the U.S., we use scanning antennas, so we're able to discount and effectively legitimize the transmission because it's coming from a space that makes sense. But in space-based, it gets to be more interesting. Anyway, it's just interesting that we're all rushing out to embrace ADS-B, and yet you look at it, and it's a 56-bit field that has nothing around it. There's no certificate. There's nothing in there, really. It's crazy. Another paper presented at the park came from Paul Stork. He's with Rockwell Collins, but he's representing what was the Air Data Service Provider at the time. And he was asked to look at the issues around SATCOM in particular, and having to do with ACARS messaging. And again, I'm just going to summarize. In fact, his words are even more cryptic, so I'll just translate what he's saying. ACARS is the data link that connects the flight deck to the ground. That's the data link that we use for pilots. We use it for flight management systems, central maintenance systems, aircraft condition monitoring systems, cabin terminals. It has been widely utilized. It is the data link on the airplanes. There's another data link, but I won't get into it right now. But by and large, all the airplanes that are connected are using ACARS. And ACARS has a checksum in it. And ACARS has an address that says it came from a certain facility. And that's about it. So as long as the bits add up, then it must come from that place, and it must be a valid message. And that's the way ACARS works. There's a certain temporal association with how the messages come. There's a sequencing, but if you're smart, you can monitor that and take advantage of it. So just something that we know, and again, we don't like to go out to the press and get the public all wound up about these things, but the data link, protocols that we have out today are a little bit thin when it comes to providing some sort of assurance. ACARS uses 3 different bands today, VHF, HF, and SATCOM. The issues that we're dealing with ACARS have nothing to do with the band, it has to do with the protocol. And this was your point, Andy. Right now we have attach points on the ACARS network all around the world. Thousands of terminals exist, and each one of those terminals can initiate an ACARS message. And there's policies in place to limit where those terminals can go, but by and large, those terminals have access into the DSP. The DSP treats all the airplanes somewhat, through policy tables. So there's a lot of opportunity of getting into these secure networks because there's so many access points around the world. And, looking forward, it's pretty clear that when we talk about controlled pilot data link communications in particular, but by and large, there is a weakness in where we're at today, in authentication in particular. And integrity and authentication are kind of a match set because you can't have authentication without integrity. Confidentiality, we're not sure. There are some concerns about revealing information in the clear. That by itself doesn't threaten an airplane, frankly. It may have commercial ramifications. It may have other things, but by and large, confidentiality doesn't drive this kind of a threat. However, we think there is good reason to keep this information hidden, and so that's a factor. This is a page out of a Boeing flight manual that shows a depiction of what you would see in the flight deck of flight control positions of one of their airplanes, a modern airplane. And this is what we would call the normal situation. This is a situation, same display, but with somewhat concerning display. The yellow, when you start to see amber, things aren't good. Okay, green is good, amber is not good. So things are starting to fail. We don't know where some of the flight control positions are. We've lost sources from them. This is what we would call a non-normal scenario. So life is good in the normals. Life is a little more challenging than non-normals. And airplanes are built inherently to deal with non-normal scenarios. In fact, we train, as I used to say as an aircraft designer, I spend 99% of my time on the 1% scenarios, and that's really true. I spend almost all of my time worrying about these corner conditions. It's not the sunny day scenarios. Those are the easy ones. It's the cloudy day and the rainy days that get you. This is a modern Boeing airplane, and what it shows is a distribution of Ethernet to manage all of the flight controls on the airplane. So the entire airplane is fly-by Ethernet. Okay, every bit of the flight controls, except for, and I'll talk about it, the direct mode. There is a backup. So there's a number of different Ethernet domains, Ethernet spheres, if you will. I don't want to call it domains because that'll confuse it. But this is what we call the aircraft control domain. When we talk about aircraft control, this is what we're talking about. This is the part of the airplane that makes it fly. And it's all Ethernet. Now, how the heck does that work? How could Ethernet be safe? It's time-triggered Ethernet. In the industry, we're calling it ARINC 664 Part 7. ARINC 664 is a specification. Part 7 is the 7th chapter, if you will, or they're actually standalone documents, so Part 7 is a standalone feature, and it describes a form of Ethernet that's called time-triggered. Ethernet today uses CSMA, carrier-sensed multiple access. So Ethernet has the potential for collisions, and so throughputs on Ethernet are not necessarily guaranteed. And that becomes very difficult when you're trying to run flight controls because you need to have regular sensor inputs provided to you. If they start to come in at different rates or they have jitter around them, it starts to throw off filters, and that gets into the quality of control of the airplane. So it's very important in a data link system on board the aircraft to distribute information in a very rigorous manner so that everything shows up exactly when it should. And if it doesn't show up, that's a problem, and you detect that as a problem, and then you can take actions on the basis of that. And it's this rigidity of communication that becomes the foundation for it to be used as a fundamental flight controls technology. And you'll see here, I highlighted it, this is from a particular company, but this chipset is certified to a level A application. So this is a piece of hardware that is not ever expected to fail in the lifetime of the fleet of airplanes. So all the airplanes, for all the years they ever fly, we never expect one of these to fail. That's the design criteria around level A. So it's pretty rigid, and again, there's a lot of emphasis around hardware as being the way to control that rather than reprogramming the software. Now, I've talked about Boeing, and you might think, well, gosh, Boeing, why did they do that? Well, Airbus does it too. In fact, Airbus invented this technology, and they call it AFDX. And AFDX is a copyrighted name, and so we call it time triggered Ethernet or whatever to dodge the intellectual property requirements. So this architecture that I described on the Boeing airplane, these exist on Airbus airplanes as well. Okay. So I mentioned the primary flight controls has different modes of operation. The normal mode of operation, happy as a pig. I mean, everything is great. There's no yellow, no amber anywhere. Everything is just going along fine. Secondary mode, things have started to degrade. You've lost a sensor package, maybe an inertial system went off, or data has failed, and so the system has dropped down. You've lost a little bit of your maybe envelope protection capabilities or some of the bells and whistles. The airplane still flies fine, and so the pilot now still smiling, but maybe just a little bit more, on their toes. So then the third mode of failure is what they call direct mode, and this is when there's been a fundamental breakdown in communications on the airplane. So that Ethernet that should never ever fail has failed for whatever reason, and we've lost the ability to control the airplane through that path. And so there is a way to revert the airplane into what they call direct mode, and this is where effectively the analog inputs from the yoke are translated into flight control positions, and the use of a big Ethernet bus kind of has all gone away, and this is following a more analog path. I'm not saying that it's all analog, but it's an analog. So the plane is still completely flight worthy. There's nothing that jeopardizes its ability to be flown, but I think this is probably the best way to think about it. You're juggling a lot of things at this point. When an airplane has fallen into this point, you're not sure what your airspeeds are. You're not sure what your altitudes are. You don't know where your heading is. You don't. A lot of things have gone wrong for you to get here, and so you're busy. And it's easier for you to drop something, for the dog to run away, or for the phone to not get answered, or whatever. And so, and that's how catastrophes tend to accumulate: is a sequence of events, any one of which probably would have saved the day, but they all lined up, and so a bad thing happened. And when you get into direct mode, you're eroding the safe margins on the airplane. So the pilots are operating on lower margins than they normally would. The airplane's in jeopardy. It doesn't mean that it's going to crash, but it's in jeopardy compared to what normal mode would be. There's a lot of acronyms on this chart. So I need to get you a sense for what this chart means, and then because you're going to see it about a dozen times, but in different permutations. So on the top are, in the big dark circles, are two different aircraft domains. And the one on the left is what we would call aircraft control domain. Now, in this case, the only instance of aircraft control that we're talking about is ACARS. So this has nothing to do with connections to flight controls or anything like that. We're just talking about reaching over to get ACARS messages. ACARS has air traffic control in it, so that's why it gets stuck over in ACD. ACD, aircraft control domain. When I'm talking about domains, these come from ARINC 664. There's, I think it's, on my head here, I think it's part 5, describes Ethernet, and within that, it describes 4 domains on the airplane. These are Ethernet domains, and the idea is that each one of these domains is an isolated instance. There's no crossover of broadcast traffic. These are physically isolated domains. There is no switch that ties these together, and that's part of the special conditions, for example, to demonstrate that you don't have these steep circuits between them. They can happen inside a box, by the way, and that's some of the things that we have to worry about. So what I've shown in the middle circle there is passenger information and entertainment services, ISE domain, or ISD. Pardon me. And in the early days, and I mean like 1990 days, we put a 6-channel SATCOM system on aircraft. We had a data channel set aside that did ACARS, and we left the other channels for voice, some of it for the pilots, some for the passengers, but they were just connected into the PSTN. You could do circuit switch data over it. I worked for a company that did that for a while, in fact, but it didn't go too far. So this is like 1990s technology. So the radio has a 429 interface that goes up into ACARS and takes the ACARS messages. And then it had, in this case, it was SEPT1, I think. typically, and we have analog actually into the flight deck, but there was a digital data bus that allowed some number of voice channels to come to us, like 24 voice channels. We only could support maybe 5. And so that's where we were today. And so the 429 information was sent down through a special protocol called an Inmarsat data level 2, and it went to the ground station, and then it went on to the service provider. So I'm just going to leave that alone because that configuration is really archaic. We've moved up a bit, in that now we have an IP-capable satellite radio typically on the airplane. This would have been Swift 64, now Swift broadband. So we're getting hundreds of kilobits of data rate capability. So there's a networking connection now, an IP networking connection extending and reaching into the IFE, probably for transaction processing, maintenance and control, not so much for internet access. There are some airlines out there doing internet access over something like a Swift broadband, but it's a tough go. Let's just put it that way. So the 429 side didn't change at all in this architecture. So this came in the mid-90s with Swift 64, and it's still out there today. This is the predominant configuration that we have out there today. So I wanted to identify how we secure these communications. And so what I've highlighted in red is the part of the link that is secure. And so what we do is we make sure, and we're mostly worried about the ACARS traffic, not as much the passenger. The ACARS traffic is secured as it enters the ground station. And then we trust that it gets safely to where it needs to go. So it's trust and policy from this point forward. Now, in the case of ACARS, we use it, here's these acronyms on the bottom. So DSP is Data Link Service Provider, that would be like an AirCar CETA. ANSP, that would be like an FAA, that's Air Navigation Service Provider. The airline transaction processor, that's your credit card company. Meteorological information, that's either sending or receiving weather information, and then IV content. So these were sort of categories of different types of end systems that you might want to communicate from the airplane. And so this ACARS traffic would come down and get to the DSP, and that path was done through mechanisms that ARINC and the service providers worked out between themselves and believed them to be secure. I'm not saying that they got this out in the air or anything. They went through quite a bit of effort to make sure that the connectivity between those two corporate enterprises is secure. And then similarly, there's a distribution network within the ACARS world. It's ARINC 620. It's a private network, and that's how that information is distributed. So there's a lot of trust that goes on here, and the weakness, by and large, the weakness with ACARS is not so much getting something picked up on the ground. The fact is, over the air, it's very easy to decode. So you could spend a day and you could be watching your ACARS messages if you wanted. It's not that hard. One thing came into the marketplace that changed things, and that's what we call the electronic flight bag. And pilots, if you can imagine, have to have approach charts and route charts, some degree of aircraft manuals. They have to keep these up to date. They have a personal set, like Jeppesen would provide it, and it's a god-awful job. Every week you'd get a stack full of revisions, and you have to open up your big notebook and substitute the new approach chart every 28 days or whatever. You'd have to do this manual process. And so that's what you're seeing here is these stacks and stacks of approach charts and procedures and so forth. And they carry these onto the airplane, or they're stored on the airplane itself. And way back when we talked about the paperless cockpit, and I liked Airbus, they changed the name to the less paper cockpit because paperless is not ever going to get there. But there clearly was an opportunity here. Boeing had tried to move this way with the 777 originally, but they had some performance issues relating to how quickly the charts could be produced. By the way, the failure modes of a chart are pretty benign. Paper charts, you can spill coffee on it maybe, or poke a hole in it, but by and large, if you've got that piece of paper, it's got integrity and it's good. But when you present that same information on a screen, there's a question that comes to your mind. Is this accurate? Is this up to date? Is this the right one? Trust comes into it, and you have to trust that the operating system's got it. So there's a little bit of baggage. That's a funny term. There's baggage that comes along with this. But so you can see the EFB over on the corner here. I lost my mouse. There it is. So there's an EFB, but here's an example of I think this was the United pilot. holding one, and then this is a Boeing built-in EFB. They come in different classes depending on whether they're basically a commercial off-the-shelf like an iPad, or are they a piece of avionics that are fully installed in the airplane. People have been writing applications for EFBs. It's just amazing to watch this. This is a list in advisory circular, FAA advisory circular that talks about EFB, gives examples of the types of applications. So this is just examples the FAA came up with. I know you can't read it, I can't read it, but there's more, and there's more. Okay, there's a lot of applications, right? And they're growing every 6 months. I've got 20% more applications in the marketplace. Now, what are these applications and what can they do? So there are three kinds of applications within the EFB. Type A, which would be appropriate for your iPad. Those are really just planning tools. Has some utility, but you're not depending on it, so to speak. Type B, you're now dependent on the FB to operate for you. And so we've already had a couple of airlines, well, I know of at least one airline that had an issue where software that went out to their FBs there was a mistake made. And so the nav database was corrupted, and suddenly that airline couldn't fly those airplanes until they could figure out what to do. They ended up taking paper charts out to the airplane to work around that problem. So where before we never would have a case of an airplane dispatch being threatened by the existence of a paper chart, we now have fleets of airplanes that are threatened by an EFB nav database or some sort of shortcoming. So we've become very dependent operationally on EFBs, where before we had no dependency on them at all. Type C, there's a lot of people that are very dedicated to EFB that know it, they know what they're doing. I'm not suggesting that this is a bad situation, but the problem is when you have disruption and it starts to impact more and more of the capability in the airplane, it can have unexpected consequences. And so as we become more and more dependent on the EFB, we're creating an opportunity for that to create new problems that we never had before. And so what's alarming to me is that Type C, we're talking about applications now that are allowed to go up to the major or even higher level. The major failure is certainly not the end of the world, but that we're up at the flight management system level now. Okay, so we've left this, give me a piece of paper, and we're now talking about functions that are at the same level of flight management in the CFB. So, interesting situation. This is how I look at the EFB. That's Pandora. That's the box. I honestly watch this space. I think there's a big target on EFB. So we've added EFB. So this is a new domain. This is the Aircraft Information Services domain, AIS. So we have 3 domains: the aircraft control, passenger information entertainment, and aircraft information. There is a 4th domain, passenger-owned devices. And the reality is, it's not it doesn't exist except for the extent that it goes into the IP. So the PODD domain, which I don't bother showing, is actually right here. It's this circle right there. So there's no benefit in eliminating that. So each of these domains is physically isolated from each other. There is an oversight process to make sure that this is the case. Now, in the design side, we have a fair amount of sophistication to do these kinds of analysis. As the airplane moves into operations and starts to get modified and so forth, the ability to do that kind of analysis may get marginalized a little bit. So understand that the airplane may have left perfectly when it was delivered, but 5 or 10 years down the road, maybe some things have changed that have unwittingly undermined some of the protections in it. And sneak circuits between the domains is the one that we're mostly worried about. And an example of where we're going to see that is devices that want to produce maintenance information. They need to get that off the airplane. We don't necessarily want to send that through the highest, most expensive pipe. We'd like to send it over the cheapest pipe. So we would like to reach over to a flight control computer to get its byte information to be sent to the ground. Well, so we're going to have a port into that device. Now that port is designed to not to have limited capabilities, but that port becomes a path into the ACD. So even though you're not physically connected to the Ethernet broadcast domains, within a box, you may see these two domains coming together. And this is something that I'm going to talk about. This is a big issue for us in the K-band world, but basically for all of the broadband radios, we've got this problem in wanting to serve multiple domains with one big pipe. But we're not there yet. So this is a multi-channel radio again, so we have different radio channels. It's one box, but it's different radio channels inside the box that do different things. So over the RF link, we can secure the channel. 5 minutes. Good. So in this case, just like it was before, we've done a good job securing the connection between the air to the ground, but we completely trust the distribution of the information once it reaches the teleport and goes into the public networks. At this point, there's no additional anything from the air side influencing the secured transfer of information. So this is where we're at today. This is the configuration that we're. And oh, by the way, I showed over here another evolution. This would be called Swift Broadband Safety, or fans over Iridium. These are using the Airing 429 interface to ACARS management unit or communications management unit, and it's converting it into an IP stream that's sent over the ground. So there's a bridging protocol that goes between 429 and IP. And so we've been able to move the ACARS off of what was effectively a high cost channel into a higher speed, lower cost channel. Still an isolated channel, but it operates at higher speed than it did before. The old channels, the fast one was 10.4 kilobits, or 10.5 kilobits. That was the fast channel we had. Now we're into hundreds of kilobits, so it's quite a bit faster. All right, so recognizing that we haven't really solved all the problems we would like to, we're undertaking some new work, and the name is still moving around, but I've really gotten to like Broadband Aviation Radio Network, the BARN. And we're writing this around the context of KU-band and KA-band radio technologies, but it has the same issue exists in all of the radios, whether it be Inmarsat, Iridium, cellular radios, wireless LAN, Aeromax. They all have the same. We basically are all running into the same problem. And the problem is that we want to combine the traffic from these three domains into one RF link off the airplane. Okay, that's the challenge we're faced with. All of the new radios that are coming into being are offering one big IP connection, not three. Okay, so somehow we have to put that traffic together and send it over this pipe and not mess it up, because we've got to maintain segmentation. The isolation between those domains has to be maintained. And so this device right here is that sneak circuit that I was talking about. So here's a device that is purposefully designed to cross and have connections into each one of these domains. Now the physical, you can isolate this physically pretty easily, but the minute you get into this operating environment, everything starts to get questionable. And so what we foresaw was, if we don't solve this problem here, we solve it in the radio. The radio is more or less an off-the-shelf device. Inmarsat, Iridium, cellular, we buy those channel units pretty much as a wholesale device, and we plug it into a box and we build a bunch of stuff around it and we call it a radio. And what we don't want to do is to go to T-Mobile and say, hey, by the way, you need to change your network to support me because I need these features for aviation. And T-Mobile's going to say, well, if you've got a lot of money, I'll listen, but probably they're going to say, take a hike. So we can't change the COTS world, the commercial off-the-shelf world. We're kind of stuck. And if we insist on changing it, we're either going to preclude certain networks or we're going to make those networks really expensive to build, because we're going to have to customize what should have been an off-the-shelf development. And so what we're trying to do is federate this function away from the radio so the radio is left untouched. And that's the point of the 848 layer, you can think of the IP as being the radio itself. And so this, as a standalone, if you will, embedded module with its own operating capability, whether it's FPGA or software driven, it would be driven to a higher level of certification, maybe a level C, compared to the radio, which might be a level E. Okay, and that's the big payoff. Now, there's more to it than just the domain segmentation. The other half of it is end-to-end, managing the end-to-end experience. As I told you in prior examples, each time we got to the ground, we got to a trusting environment. We trusted that everything was being distributed properly. We spoke to all the intermediate systems and asked them to do a good job, and they said, yes, we will. And we went home and slept soundly in our bed. But that's really not the way to go. So what we want to do is we want to find a way to span the untrusted, stay actually part of the network, and connect these corporate enterprises together without having to worry about this intermediate piece. And so we've come up with a thing called the domain organizer, the door. Remember, I called it the barn. So this is the barn door. So it's built around IPsec as a VPN technology. It's a whole bunch of IPsec tunnels. And basically, we put up a tunnel for every instance of quality of service and for every connection between a domain and an end system on the ground. It has modern authentication, integrity, certificates. It's a contemporary protocol. Software-defined WAN is the closest thing we have to it, or intelligent WAN, I think is what Cisco calls it. But these are 2015 protocols. I mean, we're really right on the leading edge for this. It supports encryption and confidentiality. It protects the radio as we'd hoped. And quality of service becomes a big issue for us. I don't want to get into the details here, but we don't do a good job right now understanding what we want to do with information when we take it off the airplane. We just kind of treat it all like bits. We don't really prefer one over the other. If we do kind of a poor job. So we're also providing sort of a modern step up in quality of service. And so what this has done now is you can see now the red is extended from the border of the domains on the airplane to the border of the enterprises themselves. And we don't have to worry. There's no trust anymore between us and across the internet. You can, the way I showed it there, you kind of see it everywhere. But here's an example of one VPN that's coming, like running the ACARS traffic going out to the DSP. So this VPN is not from the ACARS, it's from here. So this VPN can serve multiple clients as long as they're following the same path. It can be reused. You can also, as a next step, extend to where we were doing VPN from, if you will, enterprise to enterprise. You can also do VPN from end system to end system. And this is a good idea from a defense in depth approach. I'm not suggesting that you would do one or the other. I'm suggesting you would do both. And that's again, it's defense in depth why we do that. So here you can see the FB has put up a VPN that terminates at the FB. It goes all the way down to an application that is riding at a meteorological center. And then you can kind of think of what it might look like in a virtual sense. We're also looking at the onboard network between what I call the radio and the end system, the LAN. It's unprotected right now. We need a way to segment the traffic by priority, by quality of service. And so we're planning on using a layer 2 VLAN overlay to allow us to federate the traffic as it's coming out of the end system to match up with the radio quality of service requirement. All right, and now the last thing I want to talk about is software data loading. So I've been an advocate for remote software loading for a long time. And in fact, about the last 4 or 5 years, I've been really pushing the AWC to step up to provide remote software loading. So what we're talking about is today, a mechanic has to come out to the airplane. You can send information to the airplane and have it stored, but to actually load it into an LRU, avionics tech has to come out, select the data loader, put the box into a loading mode, put the software in. Then they're exposed to a checksum or a CRC, which is some god-awful number of digits, and they compare that diligently and say, yep, it came in perfectly right, and they sign it off. And that's the way we do software loading today. Of course, it relies on manual touching the airplane, which can be difficult depending on how the airplane's flying around. As we move into network security in particular, we have to be very rapid in rolling out software changes. We can't have an exploit come into be and have it take us 6 months to get out and touch all the airplanes to protect them against this kind of exploit. We need to roll it out right away. So rapid dissemination of software is very important to us, but there's a downside to it, and that is basically the foundation for network security is assuming that each LRU is designed around certain requirements, and those requirements are realized. And software loading is, of course, how that function gets to be. So if somebody changes that software, they can make it appear to have all the functions that it normally have, but maybe some extra special ones that might show up at some time, arrival in an airport, at a day, or altitude, or whatever. So it's a little scary because this now sort of bypasses almost all of the security we have in place. This sort of is a short circuit to it. And so my last slide, the Trojan bunny. That's it. I know I kind of used up all my time, but
Should we take time for maybe one question?
one question.
Eric?
Yes. Your presentation focused mostly on the network security reason, that part. But nevertheless, you spoke about the software loading, that means you were protecting more in the plane. Nevertheless, there's still a risk which is on the side, at the beginning, on the application which are feeding your information or your new software on your side. What is done on that part?
So, normal software development follows a system engineering process of writing requirements, designing software, designing tests, and having a validation verification process around that. And the functions that an LRU introduces to an airplane are evaluated. The functional hazard assessment is done to ensure that the scope of those functions is in line with the software level that it has. So I don't believe release software represents a threat. Now, you're right. We could have somebody sitting in a device and see it, but as you move up, we have to evaluate it. There has to be a test for every single line of software. Okay, it's not casual as we move up to level C and higher. So there is a review, a line-by-line review of that software. So having somebody create features at that level of software that could withstand the kind of scrutiny that it will take in the normal process, not the nefarious side, is difficult to accept. And even, well, I'll just leave it at that. It's difficult to accept because we set up the process to catch these type of things. Whether you intend to do it or whether you did it by mistake, it has the same benefit, it has the same impact. And so I think the process is set up quite well to catch those. But the bottom line is, anybody can do anything. Let's just anybody can do it.
Dharmesh, why don't we take your question and then we'll go to break.
Yeah, Peter, just wanted to get your thoughts on where do you think the OEMs are with respect to security in terms of the domain segregation of the current aircraft. There's thousands of airplanes that are flying that don't have ASDX or Ethernet capability and are just analog 429. Those airplanes will continue to fly for quite some time. And then, of course, you have the next generation airplanes that are flying. So, have they been part of the discussion
Sure.
at the forefront of
Well, yeah. So I would say that Area 64 domain segmentation is the answer to how they believe the flight controls are safe. Right? So the whole point of protecting the ACD from the other domains was exactly that. So there's a lot of weight on that point. So I've been going around to different subcommittees to talk about these issues, and it's kind of a shame, and I don't want to paint this in a bad brush, but there's a legacy that existed, which I showed you, which said that we've got FAA approval as long as we can secure it to the ground, and the FAA focus is the part with the wings. As soon as it doesn't have wings on it, the FAA doesn't really care about it anymore from our perspective. So as long as it's secure as it leaves the border of the airplane, then it's certificable. And so there's a heavy emphasis within the industry right now to say, why do we have to do this end-to-end stuff? We've already got approval for the air-to-ground piece. We don't have to do it anymore. So that's out there right now. So if you look at Iridium Next developments, Swift Broadband, they have not embraced end-to-end security as a mandate. As far as, and I'm trying to wake them up to this, and in the end, it's a hard problem. So we're starting it in the KUK band world. Aeromax is, I think, coming into alignment with us. We're working with NAS, which does cellular and wireless LAN, and I think they're coming along with it as well. So we're building a sort of a foundation of support for it. As far as the issue of are the OEMs concerned about this? Are they actively involved in this? So number one, they won't talk about it publicly. All right. So you're getting a lot of silence right now because they won't talk about this stuff. They don't see the benefit and they see the downsides. So I'm here talking to you because I'm an independent and I'm not encumbered by their edicts, if you will. But there's no way somebody from Boeing or Airbus would come up and stand here and talk to you about this in this kind of forum. But in the smaller subcommittees, we do have these people there. And I would say they're very skeptical. They basically don't believe it can be done. The ideas that we've presented, and not so much between the EFD and the passengers, because that's not really where it's at. It's as we move into the ACD that they have concerns. And so we've kind of stepped back and said, we're just talking ACARS right now. We're not trying to connect into your world of flight control computers and so forth. And that, I think, will undermine the thought, the pushback. But the bottom line is, I don't think the OEMs are on board with the idea that you can have a device spanning between ACD and AIS. But we do have, ARINC 781 has an example of it, ARINC Project Paper 771 has an example of it, and there's a couple of other examples having to do with the EFB that have been created. So we have a handful of examples where people think that they're doing a good job of maintaining segmentation between AIS and ACD, but the jury is really out there on whether that's acceptable. So it's on paper, but nobody's actually built it to their satisfaction. And the reality is we don't have any connections into ACD, so it's kind of a moot point because we're not really connected to anything there anyway. All right.
All right. Peter, thank you.